Welcome to EDU World Space.
Here, Sn is defined as, it's a sequence where the term is defined as the nth partial sum of the harmonic series. For part A, let's go ahead and show the following inequality. That Sn is no larger than 1 plus natural log of n. Okay, so first, let's go ahead and start a graph here. So first, I'd like to plot some rectangles here correspond to the terms of this series, 1 over n. So the first term is just 1. So I'll represent that with a rectangle, width 1, and height 1. All my rectangles have length 1, width 1, and then the height will be 1 over n. So the second rectangle, that height will be 1/2. And so on. And let's also draw the curve 1 over x. Where did that come from? Well, it's just a continuous version of n, replacing n with x. And this more or less looks something like this. It's always above the rectangles, but it will touch at the right corner. So if we look at, just looking at the picture here, we can see 1 over n, which is the area of the nth rectangle, so 1 over n is a rectangle over the interval n minus 1 to n on a real line. And we know the height is 1 over n. And we know that the curve will touch it at the right corner from above. So the area of the rectangle is just an. That's in blue. But then in red is the right-hand side. That's all the area of the curve over the interval. So that's why the red area is larger than the blue. So that implies this inequality here if you're interpreting these terms as areas. That's what the trick is here. Okay, so let's, and also here when I'm using this inequality, I'm using it for n at least 2, because otherwise we don't want to deal with n equals 1, because this is not a convergent integral here. This improper integral diverges, because you can see here the curve goes forever. You'd have to write this integral as limit, and your answer will be infinity. So that's why I'm only doing this inequality for n at least 2. So let's go ahead and use this inequality for all of these n's and then add them all up. So I'm not writing the whole harmonic series, the partial sum. I'm excluding the first term because, again, n was at least 2. And now using that inequality that we had n minus 1 times, where again, the inequality that we had was the form so we're just using that for each of these corresponding terms, and so on. However, if you look at the right-hand side, you'll notice these all have the same integrand. And we could use a property of integration, integrals, that if you add the integral from a to b and then from b to c, that's the integral from a to c. So if we use this property multiple times on the right-hand side here, we can rewrite this right-hand side as integral from 1 to n, and then dx over x, which becomes natural log of n. And then now add 1 to both sides. So by both sides, I mean the left-hand side here, left-hand side, and then right-hand side. We get this is less than or equal to, and then 1 plus natural log of n, and this finishes part A because the left-hand side here, after adding 1, this is now equal to Sn. So let's go on to the next page for part B. So although series diverges, we'd like to show that it diverges very slowly. So what that means is that you have to add a lot of terms, and even after doing so, your sum won't even be that large. So here we'll show two inequalities. One, that if you add 1,000,000 of these terms, the millionth partial sum, that's a 1 with 6 zeros there, 1 over I, or S sub 1,000,000 if you want to write that. We want to show that's less than 15. And then we'll also show that if you had 1,000,000,000 terms, it actually is not much larger. In this case, it'll be less than 22 actually. So these confirm that even though this is an infinite sum, it just happens to grow very slowly. Okay, now for part 1, well, we'll go ahead and use the inequality. So remember what we showed in part A, Sn, 1 plus natural log of n. So go ahead and just plug in 1,000,000 for n. And this will be less than or equal to, and then we'll have just plugging in the same n on the right hand side here. Let me write that now as 10 to the 6th. And then this is 1 plus 6 ln 10. And a calculator gives about 14.8, which is less than 15. So that confirms the first part here, part B. Similarly, using this again, plug in 1,000,000,000 for n. And here I'll just write it in the scientific notation. That's 10 to the 9th. 9 natural log of 10. Now we'll go to the calculator. This is about 21.7, which is indeed less than the desired 22, and that confirms the second inequality.